Good day, and thank you all for coming to my presentation, two-dimensional mathematical modeling of flows in thin-film composite membranes. Just to give you all a background on the research that is being done here. So this is research that we're doing into wave-powered desalination, and the research has been broken up into two parts, wave-powered and desalination. This presentation here is on some of the work that we have done on the mathematical modeling aspects of the desalination of desalination systems, of desalination membranes rather, which actually came about as a result of the fact that a lot of models that we would have seen in the literature were a bit oversimplified for the applications of wave-powered desalination, in that they assumed constant rejection properties of membranes, which is not necessarily the case. So when we look at membranes, the literature would suggest, well, in fact, there are three areas that we have to look at when we're considering RO membranes. The first area is flows across membranes, concentration, polarization, and hydrodynamics within the feed and permeate channels. The typical analytical models that exist or that have been created typically only ever considered the first two aspects. With the advent of computers, we have now been able to make use of CFD-based analysis, and now we could actually start to take into account the hydrodynamics within the feed and permeate channels. But as I mentioned before, the problem with a lot of the models, as shown within the literature, or that we could find within the literature, is that they make the simplifying assumptions that membranes operate at constant rejection properties. All right. So for our model, we made a number of assumptions, 9 of them in total. Of interest is the first two. The first ones being that we're only taking into account a two-dimensional system. And the reason for this is that if we look at, if we try to expand into a three-dimensional system, the computational requirements of such models are quite extensive. Secondly, we assumed that this solution diffusion model was true, and that is that the membranes that we're looking at are non-porous. We would have made also various assumptions in terms of water permeability, bulk solute rejection, laminar flow conditions. We assumed that the fluid flow was incompressible with constant viscosity and density, that there were, in fact, no reactions that took place between chemical species. We assumed constant diffusivity, and that the process was isothermal. So in developing our equations, we would have had to have made two changes to the established equations found in the literature. And these two changes were made to the pseudo-Darcy equation for water flows across, or water flux across the membrane. And the second one was some small modifications made to the solute flux across the active layers of our membranes. In these equations, alpha and beta are semi-empirical relationships that were developed to account for the effects of pressure and concentration on changes, changes in solute flows, solute and solvent flows. It is to note that the literature does in fact agree that this assumption of linearity is not in fact true, and that there's sufficient evidence within the literature to show that flows, water fluxes across the membrane, as well as solute fluxes, are also non-linear. Right? When we were specifying our equations for our permeate and feed channels, we assumed that the channels are given by the incompressible forms of the continuity and Navier-Stokes equations, and that the solute flows in our feed porous support layer of the membranes and permeate channels were given by the equations, by the transport equations, assuming both effective and diffusive components. Right. So once we had developed our model, we had to validate our model. So we would have done our model validation against Kim and Hoek from 2015, and in their setup, they had an experimental setup in which they considered 3 operating pressures at 3 average cross-flow velocities at 3 concentration levels, for a total of 27 data points. For their setup, this is what the model geometry looks like for their setup. So they would have had an inlet, pre-channel, outlet, and permeate channel. And how this varies from the standard spiral wound membranes is that our permeate channel out goes down rather than across or into the spiral. Right? We would have specified Navier-Stokes continuity transport equations in our inlet, pseudo-Darcy and transport equations in our membrane, and Navier-Stokes continuity continuity and transport equations in our permeate channel. Right. So before we can actually go about doing and looking at our simulations, we had to establish grid independence. For this, when we established grid independence, we would have assumed just basic values. So inlet in this case was 1136.3 kilopascals. Our average velocity within the feed channel was 0.42 meters per second, a concentration of 50 moles per meter cube. Our diffusion coefficient through the active layer of the membrane was assumed to be 400 by 10 to the minus 15 meters per second, meters squared per second. And alpha and beta in this instance was assumed to be 0. Our total number of elements having reduced our mesh, sequentially reduced and continuously reduced, was about, we found grid independence at about 6.7 million elements. Right. Having done this, we would have then conducting the simulations for the various experimental data points as presented by Kim and Hoek. But before we could have done that, we actually had to calibrate our diffusion coefficient through the active layer of the membrane. This was done for one of the experimental points and was found to be 380.3 by 10 to the minus 15 meters squared per second. All of the simulations were then conducted, and for these simulations, alpha and beta ranged between -1. So for alpha, it was -0.176 by 0.176 to 0.038, and for beta it was -197 to 0.072 respectively. Right. So these simulations were done for all of the experimental points from Kim and Hoek. All right. And the takeaways from this was that based on our simulations, what we found is that the average error was -0.6 plus or minus 2.6, and the average predicted error for concentration was 0.7% plus or minus 7.6%. These were done at 95% confidence intervals. All right. Now, the thing with desalination membranes is that typically all desalination membranes that come make use of feed spacers. And the reason for this is firstly to keep the membranes of whatever desalination system apart, of the membranes apart. The second one is to promote shearing at the membrane surface to reduce the effects of concentration polarization. To be able to model the concepts of feed spacers or the distance between feed spacers, we used the geometric ratio by Kutsu, Yantis, and Carabellas from 2007, which is defined as the distance between individual spacers and the diameter of the spacer. For ease of use, what we assume is that the diameter of the spacers half the height of the membrane feed channel. Now, having conducted further simulations, right, we would have looked at 3 spacer types, namely submerged spacers, cavity, and zigzag. And what we found is that once we use, independent of whatever spacer type we have an increase in permeate flows and a reduction in solute flows of permeate concentration. What we also found is that the max wall shear stress increases significantly, and the value shown here is in fact in line with the literature. What we also further found is that submerged spacers, again, in line with the literature, are probably the best type of configuration to be used. So in conclusion, we developed a 2-dimensional mathematical model for thin film reverse osmosis membranes. Our model in this instance actually accounts for all of the various layers of the thin film RO membrane, and that our model also accounts for the effects of feed spacers. This is just some of the references that we used for this particular presentation. Thank you all very much. If you all have any questions, thank you.
Thank you, Mr. Maharajh, for your nice presentation about the membranes, RO membranes. So I'm not seeing any question in the chat list, but if anybody is having any question, can ask Mr. Maharajh. The floor is open now. So, okay, then I'm asking the question about RO membranes. You worked on RO membranes. What kind of geometry do you recommend? Geometry as well as the thickness, etc. All these kind of things means depending on the concentration of the water. Yeah.
So you're asking about the geometry of the membrane itself?
Yeah, yeah.
Okay, so the membranes themselves actually come as a spiral wound membrane. So these are standard geometries found in the industry. The reason being that cross-flow process has actually been found to be able to yield the most amount of permeate production whilst reducing concentration, as well as there are mechanical benefits by using that approach. So that's actually standard throughout the industry.
No, that is standard. Yeah, that is standard. Means, did you do any work like the changing of the thickness as well as in the spiral model? If you want to make some changes to make the more surface area or kind of thing.
So the problem with this is way back when we actually, so the desalination industry was actually looking at expanding or looking at the surface area as one of the considerations. So they went from 4.5-inch membranes way back in the 80s. They went up to 4-inch, 8-inch, and then they tried introducing 16-inch membranes, where the effective area was significantly was a lot. The problem with going and scaling up with that is that you have to then have the flows going through the membranes itself, and that there actually can be issues with, for example, the presence of voids within the membrane when you start to ramp up to 16-inch type membranes. So typically, if you're going to do it, especially within an industrial setting, you're going to want to stick to your 8-inch membranes. For the application of wave power desalination, you might actually want to go lower. And the reason for being is because we're directly coupling that with wave energy, you're going to have a near pulsating inlet pressure. And so you're not going to be able to necessarily maintain your flows across your membrane. And so smaller might actually be better in this case.
So a lot of parameters. Anyway, thank you very much for your answers and nice presentation.
Thank you very much.
Thank you very much. Yeah.